Alright, ladies and gentlemen, in this video we are opening up our discussion of Chapter 3 of our pre-calc talk, and we're going to be looking into exponential functions and their graphs in this particular lesson. Now, this video is going to be focused highly on just some of the characteristics of exponential function graphs. That's really what the main focus is. There's not going to be a whole lot of examples or anything necessarily like that. You're just going over the characteristics and starting to dive on into what do we see from exponential functions specifically. Okay, so the goals overall are to recognize and evaluate exponential functions with a base A. We're going to graph the exponential functions, like I said, which is the high focus of this video, and then we're going to use it with base E, and then we're also going to go ahead and look into some exponential functions with some real-life application, which is my favorite part because it starts diving on into some money, some finances and things like that, where we see exponential functions in real life. So, first and foremost, opening question, what do you think an exponential function is? Don't dwell on it too much. The question is not a trick question. It's actually a very basic question. An exponential function. Well, simply, an exponential function is a function that has x in the exponent. Yes, you got it, right? So, how is it utilized? What does it look like? What are these bases that we talk about? Well, kind of refresher course. Don't forget, when we have a base, the base is the number, and the exponent is what is being raised to, right? And so for an exponential function, we have a whole number or a fraction or some kind of real number with base A, all right? With the restrictions that A is greater than 0, not equal to 1, because everything equal to 1 is going to end up being 1 itself. Raised to 1 is going to be itself. So that's kind of answers that question down here at the bottom. So if A is 1, 1 to any power is going to be 1, so it kind of defeats the purpose of an exponential function with any kind of growth or decay. All right, so we have our base A, we are raising it to that exponential of x, okay? All right, so let's keep pushing on forward a little bit. So again, remember the focus of this particular video is nothing mind-blowing or anything like that. It's literally just we want to focus on the characteristics of what the base, how the base is affecting the graph, and how really does the base affect the growth or the decay of an exponential function. So what I want you to do for a sec is just, I've given you some x values here, and I challenge you to pause the video now and either just on your calculators or actually take the time to freehand draw this, is graph these two different functions, f of x being 2 to the x and g of x being 4 to the x. And with a focus of just being ready to think and describe what the differences in these two graphs really are. Seeing what the differences of those two graphs are actually going to be. So, pause the video and let's take a look. Alright, so hopefully you've had some time to graph the functions, and I've gone ahead and just put them on the calculator for us. And so I pulled up my 84 emulator here, and I want to kind of just show the two different functions, okay? So what you see in blue right now is our f of x, and that is 2 to the x. And so g of x is 4 to the x. So think about it. Answer the question. What really is the main difference in these two functions? Well, my goal of asking that question is to really kind of prep you to understand is what's causing the change is the base. And what's the base actually kind of doing? Well, as you can kind of see, as we have a higher base, we are approaching the higher y values much more rapidly, right? Think about it. The bigger the base, the number you put in for x or input for x is going to return a higher or greater output faster than it would if it was like 2 to the x, right? And so this red graph 4 to the x is quickly approaching positive infinity faster than our blue graph is based on the base itself. Okay, well, now at this time, do the same thing. Now, if you graphed it on paper, do the exact same thing, but now use the same values and graph 2 to the negative x and 4 to the negative x and see what happens. So pause the video, do it. Pause the video, see what happens, and give it a way to find a way to once again describe the changes now that we have negated the exponent. Alright, so you had some time to kind of make some decisions on your own, but I've gone ahead and graphed the other two as well. And so now we can see the black graph in here represents our 2 to the negative x, and then our pink graph represents the 4 to the negative x. Now this makes sense. We should simply expect these to be symmetrical about the y-axis, because what really happened, all we ended up doing was just making that reflection about it, right? That's all that really ended up happening, specifically with our change of negative x. That's it. That's all we really did. All right? And so hopefully we can kind of see what's happening in the change by negating that exponent. Again, we're just simply reflecting the graph over the y-axis. It's really all that ends up happening here, and it ends up being symmetrical on both sides as well. So hopefully we've seen a little bit of insight into what the graphs kind of look like specifically. And so now what I want to do is I want to talk about some more of the characteristics. So what I challenge you to do right now is, before you see this chart filled out, pause the video and see if you can fill out these charts on your own. The domain, the range, the intercepts, the increasing or decreasing intervals, the asymptotes, and any continuity for a to the x and a to the negative x as well. Give these a shot on your own and see what you come on up with. Well, hopefully you've had enough time now to give a shot at these different characteristics. So let's go ahead and actually fill out these two charts. So the domain, well, let's think about it for a sec. From a to the x, all right, we just saw for when it was 2 to the x or 4 to the x, whatever it was, all right, there was no limitations on that value for x, so we went from negative infinity to infinity. Well, did it hold true for a to the negative x? Yeah, all we did is reflect it, so the same thing happened. Well, what about the range? Well, the range is specified based on where specifically it's never going to cross on over. Well, what we ended up seeing, guys, is that range, we were never going to cross over the x-axis, right? We were approaching that x-axis, but we never got there. So we went from 0 to infinity, right? And did it change for the negative x? No. It swapped over the y-axis. It reflected over the y-axis, but it didn't sit there and change the approach, right? It approached the x-axis the entire time, and that was where it was going to all stop. That was it. There was nothing else happening there. All right. What about any intercepts specifically happening? Well, we know it's not going to cross the x-axis, so we know we're not going to have any x-intercepts. But we have a y-intercept. Where at? Well, we have a y-intercept specifically when x is 0, because when x is 0, that's going to give us our value of 1. So we had 1 at 0, 1, and the same thing here, a y-intercept at 0, 1 as well too. All right, we've seen a pattern here for a to the x and a to the negative x. Interesting. All right, so now increasing or decreasing. Well, this is just basic understanding is, do you know when we're seeing exponential growth or exponential decay? Well, in the example where we have positives, we are approaching positive infinity, not coming from it. And so this would be increasing or showing growth, and this was the opposite. We were coming from positive infinity and approaching 0, and so that was showing our decreasing intervals. What about asymptotes? Well, we just already talked about that we were approaching specifically, right, that horizontal asymptote at the x-axis. So the x-axis will show our horizontal asymptote here. And then what about continuity? Any forms of continuity? Remember, it means to be continuous. Remember, can I take my pencil throughout the entire graph and not make any changes, pull my pencil up at any time? And if you remember what these graphs did look like, I mean, we definitely were able to take our pencil from the top all the way down to the bottom, just continue it on through. So yeah, we are continuous on both counts. All right, so hopefully that helped us out a little bit as to what to expect from some of these graphs. So now let's take a look into what can happen when we start making some changes in the graphs themselves. All right, so we have a function, 3 to the x. I have 4 scenarios, and what I'm saying for us to do here is I want to create a new function and figure out what the change of the new function is going to be. So f of x minus 1, that means wherever I see an x, I'm supposed to substitute x minus 1 on in. So my new function is 3 to the x minus 1. Well, what does this actually represent for us? Well, in an example where we have to the x minus 1, well, what are we doing here? Remember, it's kind of the opposite of what you see. So x minus 1 is really going to show us a shift 1 unit right. All right, so we have a shift 1 unit right. What about f of x minus 2? Well, that's the entire f of x and all of that minusing 2. Well, what does that represent? Remember, when it's outside of the function, that's a change vertically. And so we are shifting 2 units down. And remember, when it's a vertical shift, it's exactly what you see, not the opposite. All right, so I challenge you, pause the video now and see if you can do the last two, negative f of x and f of negative x. Pause it, give it a shot on your own, come back and see if you're right. All right, let's see what y'all came on up with. Negative f of x, well, it means the opposite of our original function. Well, when we take an opposite of our original function, what did we ended up doing? So we're changing all of the y values, putting the opposite of f of x. That means we are reflecting, what do you think, over the x-axis. And then lastly, f of negative x, which means that we are throwing a negative x in every time we see an x. So what does it show when we actually throw the negative x on in there? Well, again, a reflection, but which time? Well, this time we're looking at a reflect over the y-axis. All right? So some changes and some shifts that we are dealing with in our functions. Last part of this video, guys, is to dive on into the natural base of e. Now, we're going to spend too much time on it because we have already been kind of talked about natural base e plenty of times on in the past. But kind of a refresher course, it roughly is 2.71, right? So roughly 2.71, 828, so on and so forth. We call it the natural exponential function, right? It's a natural base e. It's a natural exponential function where the base is e, so we are raising e to the power of x, okay? So kind of challenge yourself for a sec. Think about it. What is the graph of f and the graph of g that you see on the screen right now going to look like? What are the changes that are going to be made because we have a leading coefficient by e of 2, and then 1 of 1/2, and then we have a negative exponent versus a positive exponent. So think to yourself, what are those changes actually going to be? Well, hopefully you were able to come on up with some of the characteristics that we talked about. Where in an example like where the red graph is about to show on up a negative 0.58x, a negative exponent, we should be expecting a reflection over the y-axis, and so we should be seeing a decreasing interval happening on in there. Well, what about here, an example like this? Which one's going to be reaching those limits faster, right? Well, because we have 2 times the natural base, or 1/2 times the natural base, we're going to have a steeper function in blue versus a not as steep function in red. So let's take a look here. So as you're looking through these couple of graphs that we're dealing with, guys, so again, just understanding what some of the concepts specifically are. All right, when we have that negative exponent, we are decreasing and approaching that x-axis, and then here we are coming from the x-axis and approaching positive infinity to show that growth in there as well. All right, guys, that's going to wrap it on up for this video. Again, the goal was to really just focus on some characteristics and diving on into what to expect with exponential graphs. Now, we're on to the next video, in which we're going to start diving on into some applications. On to the next one.